Hello everyone. In our last lecture, we studied how when we access shared resources, in our case it was global data, through multiple threads in parallel, it can cause race conditions in our program. Okay, so race conditions would basically make the behavior of our program indeterminate, and that is not a good thing. Okay, we are never sure what will be the output of our program. So race conditions are bad, indeterminate behavior is bad, okay, and multi-threaded programs have a very good chance of having race conditions and indeterminate behavior, especially because we need to share data between threads, global variables, and manipulating those global variables in parallel from different threads could make our program misbehave, could cause race conditions and indeterminate behavior in our program. So how can we avoid this indeterminate behavior or race conditions? Again, in our last lectures, we saw that if the critical sections of our code, remember the critical section was that part of our code which was accessing global variables and which, if run in multiple threads in parallel, can result in race conditions or indeterminate behavior. Okay, so critical section, I repeat again, critical section is that part of our code which is accessing global variables and which, if run in parallel in multiple threads concurrently, can cause race conditions or indeterminate behavior in our program. Okay, so to avoid race condition, the solution that we discussed was that these critical sections should be executed in mutually exclusive fashion. Okay, so even if they are running in multiple threads, we should make sure in our program that they are never run concurrently in multiple threads. Okay? So multiple threads should run our critical sections in a mutually exclusive fashion, which means if one thread is executing the code of critical sections, then no other thread should be allowed to execute the code of that critical section. Okay, so at any given instance, only one thread should be in the critical section part of the code. Okay, we should stop other threads from entering into critical sections. That way, we will make sure that any thread that executes the critical section executes it atomically, and at that time, no other thread is executing the critical section part of the code, and this way, shared data would be accessed sequentially, or only one thread be accessing shared data at any given moment. So to implement this mutual exclusion or implement this atomicity, to implement mutual exclusion in our program, we have some facilities from operating systems, and one of those facilities or one of those structures is called locks. So we'll see what locks are and how do they help us implement mutual exclusion in our program. So again, as we saw earlier, that we can create multiple threads, but the scheduling of those threads is not in our control. Okay, and it was this indeterminacy of scheduling which is basically causing the executions to the instructions to execute in multiple orders, and some of those orders are bad and can result in race conditions. Our example was counter is equal to counter plus 1. Here is balance is equal to balance plus 1. It's the same thing. And critical sections, because multiple threads enter the critical section simultaneously, this caused indeterminate behavior or race condition, and we have to avoid it. Okay? And critical sections were being interrupted in the middle. Okay? That's why we are emphasizing on atomicity, that critical sections should not be interrupted in the middle, and even if they are interrupted in the middle, no other thread should be allowed to enter the critical section if another thread is already in the critical section. So again, we are trying to make it mutually exclusive, and we'll see how we can achieve it, by making them atomic. So how do locks help us achieve this? Locks are basically constructs or data structures that are provided by operating system or some other libraries. So it's a data structure, and there are two operations defined on locks, two main operations. One is that we can acquire a lock by calling a function on a lock. A lock is a data structure. We can create a variable of type lock, okay, and we can perform these two main operations on that variable of type lock. One is to acquire a lock. We can call a function to acquire a lock and pass it that lock variable. So by acquiring a lock, we mean that getting access to a lock. And the implementation of locks is defined in such a way that only one thread can acquire a lock. So let's say multiple threads call the function to acquire the same lock simultaneously, okay, concurrently. So the implementation of locks by the operating system ensures us that only one of those threads will be allowed or will be able to acquire the lock. All the other threads would be unsuccessful in acquiring the lock. The operating system guarantees us this. So we can acquire a lock, okay, and if multiple threads try to acquire the same lock, then we are guaranteed that only one of those threads will succeed in acquiring the lock. We can acquire a lock, then we can do something with it, and in the end, we can perform this release operation on the lock. Okay, so we can call a function and pass it the lock variable, and it will basically release the lock. So between once we have acquired the lock and until we have released the lock, we say that we are holding the lock. Okay, holding is a term that we have the lock with us. Okay, so we have acquired the lock and we have not released the lock yet. So we are holding the lock. So when again we saw that we discussed that multiple threads, when they try to acquire a lock simultaneously, only one of them will succeed. And once, let's say, we have acquired the lock, our thread has acquired a lock, and other threads try to acquire the lock while we are holding that lock, even those threads, they will not succeed. Okay? So lock is guaranteed that only one thread will have that lock at any given time. And once we release our lock, then that lock would be passed to another thread. Okay, so only one thread can acquire a lock. The implementation of the locks by the operating system guarantees us this, and we'll see later how this implementation is implemented. But for the moment, we'll first study how to use locks to achieve mutual exclusion, and then in the later part of the chapter, we'll see how locks are implemented by the operating system. Okay? So locks basically have two operations defined: acquire a lock and release a lock. Again, only one thread can have a lock at any given time. So we will use locks to protect our critical sections in multiple threads. How do we do this? Let's say we define a variable mutex of type lock. So this behavior will have the behavior of locks. So this variable mutex will have the behavior of locks, which means we can acquire and release this variable mutex. Because it's a lock, it will behave as a lock. So a lock can be acquired and released. So we've declared this variable called mutex for mutual exclusion. So in all our threads which are using this critical section, remember the part of code that accesses global data and is run in multiple threads in parallel and concurrently. So counter is equal to counter plus 1 was our critical section in our last code. So let's say here it's balance equal to balance plus 1. So in all our threads, we will basically define this protocol that before entering a critical section, which means before executing the code of the critical section, every thread must acquire this lock. Okay, so acquiring a lock here is this is function lock, which is used to acquire a lock. So we'll be passing it this address of this variable mutex, which is of type lock. Okay, so here we are trying to acquire this lock mutex. Okay. So what happens is, okay, let me first define the protocol. In all our threads, the protocol is every thread before entering the critical section, it should acquire a lock. And only after it has acquired the lock, it can go and execute the critical section. It can enter the critical section only after acquiring the lock. So once it has entered the critical section, it means it has already acquired the lock, and it can basically execute the critical section. And after executing the critical section, it should release the lock. Okay, so release here is this function unlock. We pass it this variable mutex of type lock to release this mutex. Okay, so the protocol is before entering critical section, we should acquire the lock. Every thread should acquire the lock before entering critical section, and after finishing a critical section, the thread should release the lock. And this lock is basically global variable and it is shared between all the threads. So all the threads can access this lock. So now we say that our critical section is protected by this lock. So what happens is basically, let's say multiple threads are running this code. With this protocol has been defined in multiple threads. They have critical sections and they are running in parallel concurrently. So every thread will follow this protocol when accessing the critical section. So let's say multiple threads try to acquire this lock simultaneously. So multiple threads call this function lock on this variable mutex. The same variable is being used in all the threads. So as we discussed right now, the implementation of locks guarantees us that only one of the threads will be able to acquire the lock. Okay? For all other threads, the function lock will not return, it will block. The function lock returns only when lock has been acquired. Okay? Until the lock is busy or is being held by another thread, this function lock will block. Acquire function will block. So multiple threads, let's say T1 and T2, try to enter the critical section, and since they are following this protocol, they will first try to acquire the lock. So this lock function will return only for one of those threads, either T1 or T2, because operating system guarantees us that when multiple threads try to acquire a lock simultaneously, only one of them will be succeeding. So let's say thread T1 is able to acquire the lock and thread T2 is not able to acquire the lock. So thread T2, this lock function will block and it will not return until it has acquired the lock. Okay? So thread T2 cannot enter the critical section right now. Thread T1 has acquired the lock, so its lock function will return and it will enter the critical section and it will basically execute the code of critical section and do balance equal to balance plus 1. Right now, when the thread T1 is in the critical section, thread T2 cannot enter the critical section. Why? Because the lock is being held by thread T1 and thread T2 cannot acquire the lock now. If it tries to acquire, it has already tried to acquire the lock and it is blocked. And meanwhile, if another thread T3 comes and tries to acquire the lock, it will also block because a lock can be acquired by only one process, and right now T1 has already acquired the lock. Okay? So again, T3, since it is following the protocol, it will also be unable to enter the critical section and it will block. Okay? So you see, by locks, we are achieving mutual exclusion in the sense that only one of these threads is in the critical section, and if another thread tries to enter the critical section, it will block because it will be unable to acquire the lock. Okay? So we have achieved mutual exclusion. So thread T1 is in critical section and it can be sure that it is the only thread in critical section. It can relax, it can basically increment its shared data as much as possible, and once the critical section is finished, then it can release the lock by calling unlock in this function mutex, on this variable mutex. Okay? So once T1 has released the lock, then T2 and T3, those two threads, they were waiting for this lock. So one of those will get the lock. Okay, so either for T1, T2 or for T3, this lock function which was blocked, it will return, and let's say it returns for T2. So T2 will now get the lock and T3 is still waiting. So again, T2 will be the only thread in the critical section. It will execute its critical section, and meanwhile, if T1 again tries to acquire the lock, T1 will block this time because T2 is using the lock. Okay? So again, T2 will update or execute its critical section alone in a mutually exclusive manner, and after that it will release the lock. So I hope it is clear that if the behavior of the lock is provided by the operating system, then using locks, we can protect our critical sections by locks and make sure that only one thread enters the critical section at any given time. Okay, so therefore we'll be able to achieve mutual exclusion and atomicity by using locks in our program, and we can avoid race condition and indeterminate behavior in our program. Okay, so mutual exclusion because only one of these threads will be at any given time, and atomicity because if thread, let's say T1 has the lock and it is in critical section, and an interrupt comes, and T1 is descheduled. Critical section is not finished, but T1 gets descheduled and T2 is scheduled. T2 is scheduled, but T2 will not be able to enter its own critical section because it cannot acquire the lock because lock has been acquired by T1. Okay, so no other thread will be able to enter the critical section, and the thread T1, when it will be rescheduled again sometime later, it will then continue its execution and finish its critical section and then release the lock. Okay, so for T1, the critical section was executed atomically as if there was no break because no other thread was able to enter the critical section during this time. Okay. So this is how locks help us achieve mutual exclusions and really avoid race conditions. So this is, again, we have discussed all this. Lock is a variable which can have anywhere two states, available or free or unlocked. This is a state when no thread has acquired a lock. The lock is free. No thread is holding the lock. Okay. It can be either in this state or it can be in the state acquired, where some thread has already acquired the lock. Okay. So when we call lock on a particular lock variable, if the lock was in free state, we will be able to acquire it. But if, and now the once we have acquired the lock, the state of the lock will now be changed, and it would be changed to acquired, held, or locked. But if we call lock function on a lock variable which has already been acquired, which is already being held, then our function will block. Okay, so this lock function, which is used to acquire the lock variable, it will block, and it will not return until it has acquired the lock. Okay, so since some other thread is already holding the lock, so our function to acquire the lock will block, and it will stay blocked until that particular thread releases the lock and lock is given to us, which means we acquire the lock. Only then we will be able to return. So we can release an acquired lock by calling unlock on it. All this we discussed in the last slide. So locks basically provide not exactly control over scheduling, but somewhat control, minimal amount of control over scheduling. Okay, because we cannot control when our thread is scheduled and descheduled. But what we can control is that while our thread is in critical section, no other thread can enter the critical section even if they are scheduled. Okay? So locks help us achieve this mutual exclusion. So fine-grained locking versus coarse-grained locking, again, it's a term that we use is that the critical sections that we are protecting by locks, they are either very small or very big. Okay, are you protecting using locks to protect big portions of your program, which means your critical section is very big, or are you using locks to protect very small portions of your code, which means your critical section are very small. Okay, so fine-grained is on a small scale, coarse-grained is on a big scale. We'll see an example in next chapter. So pthread library also provides locks. Here it provides you a data type pthread_mutex_t, which is of type lock. Mutex, as we said, for mutual exclusion. So in pthread, locks are called mutexes. So of this type, we'll declare a variable. You can give it any name. Here it's called lock. So we have declared a variable lock of type pthread_mutex_t. Okay. So this variable now behaves like a lock. We can initialize it. I mean, we should initialize it with this pthread mutex initializer, and then we can protect our critical sections by using locks. So here, whenever we want to enter a critical section, we acquire a lock. then we execute the code of our critical section, and then we release the lock. Okay, so all threads should follow this same protocol if we want to achieve mutual exclusion. Okay, so all threads before entering the critical section, they should acquire this lock, then they should execute the critical section, and then they should, after executing the critical section, they should release the lock. So if all threads follow this protocol, then the behavior of locks guarantees us that only one thread would be able to acquire a lock at any given time, and therefore for only one thread this function will return and they will be able to enter the critical section. For all other threads, while this thread is holding the lock and is inside its critical section, all other threads, if they try to acquire this same lock, this acquire function will block, okay, and they will not be able to enter the critical section until this thread finishes its critical section and releases the lock, and then lock will be given to one of those waiting threads, and then only that one thread can enter the critical section. The other thread would be still waiting. Okay. So with locks, we are guaranteeing that only one thread enters a critical section at any given time, and therefore we achieve mutual exclusion and avoid race conditions and indeterminate behavior. So you can see here this pthread function. Here p is small and this p is large. Okay. So with the original pthread library has functions starting with a small p. These functions with capital P, these are defined by the author of the book. They are wrappers around the functions of original pthread libraries, and they do some error checking in their in this wrapper functions. Okay, so you can see or find this code of this wrapper function on the author website, or the book's website. Okay, book's website contains links to codes on GitHub. If you are using pthread function, here it should be a small p. Okay, if you are not using the book code, you are using pthread library code, then it should be a small p. Okay. So pthread mutex underscore lock is used to acquire a lock, and only one thread will be able to acquire this, and pthreads underscore mutex underscore unlock is used to release a lock. Okay. So locks help us achieve mutual exclusion. Now we can go to the implementation of the locks, but let me finish this video here, and this we can do it in another video. So I'll stop the recording.